if that's the positive direction of I initially starts going this way, and then turns around and comes this way, right? And we're using di by dt to get the value of the EMF, right? So the di by dt goes from negative to positive to 0 in between. Okay? So those numbers are important. Also, the value of the I is negative through all of this cycle, and I is positive every place else. From here on up, I is positive. So that means you have to draw your picture appropriately to the directions of the magnetic field. If the current's going this way, it's coming out of the board above the wire and going into the board below the wire. If the current's going that way, it's going into the board and out of the board below, right? Via the right-hand rule. So it says, the wire in the arrangement, A is 12 centimeters, B is 16, so it's a 16 centimeter square, and I is 4.5 t squared minus 10 t, looks something like that. It says, find the EMF in the square loop at t equals 3. So obviously we're going to be using this guy, right? Just want the EMF in the loop. So it's just Faraday's law of induction, right? But we need to get the changing flux as a function of time. And then it asks, what is the direction of the induced current in the loop? So you can plug 3 in there, and that's the easiest way to do it, and figure out where it is. Is 3 here, here, here? Where's 3, right? That's the simplest way to do it and find out where you are. Then you can draw your picture appropriately. I'm going to make the assumption that it's out here somewhere. Not necessarily accurate. Yours needs to be accurate, right? If I assume it's over here, then I is positive, which means I is going this way. Then I would have coming out of the board, and then less. Coming out of the board, and then less. Why am I doing that? Because I know that B for a wire is going to be mu naught I over 2 pi r. But you must prove it because it's not previously proven. Might as well use Ampere's law for that part though, right? Because it's got symmetry. It's a long straight wire. Okay? So you've got that, and then you're going to need to take into account that that R is now either a Y or an X. Which one is it? Is the magnetic field varied because of the wire varying in the Y direction or the X direction? Y direction, right? So basically you'll be able to show that B is equal to mu naught I over 2 pi Y. Is this sounding familiar? Like the one I did, right? It has tie-ins to that, right? And so with that, then you're gonna plug that into your flux integral. Is there a Y dependence to the integral, to the B? So am I going to have to take that into account in my dA? So my integral of dA, because there's a Y dependence to it, is going to have to convert to an integral of a Y, right? So it'll be something x dy-ish, and you'll have to draw that. Is that the horizontal one or the vertical one? Right? If I have a thin slice of differential area, differential thickness dy, and length x. Looking familiar, right? So you'll have to convert that dA because of this to dy. But then you say, like, wait a minute, what about the time dependence? Because this is going to be d by dt of the flux. dA is going to be converted to dy. B is going to be converted to a function of y, as listed here. So what does the d by dt apply to? What causes the flux to change? If this is the equation of the B, and the area is not changing, and the angle is not changing, the B better be changing. What specifically is making the B change? With time, not with distance, with time.
Current.
So the d by dt will be pulled in and applied to the current. Can you get the slope of this function in 3 seconds? I think you can. I have confidence in your calculus abilities to do that. And then the dIdP will simply be the slope of this guy at 3 seconds. How do we get the slope of a function? Take the derivative. All that fun stuff. So let's do it. Do it. So that's the approach you take to this. When you're done then, you'll have to break the flux integral down. That integral over y has got to take into account this value and this value. But as I mentioned last time, you're going to make an argument that the positive flux and the negative flux cancel out here to this distance of, how do they label that top distance? They didn't give it a label. BA, so I guess that's B minus A. Right? So down here to a B minus A distance, you start your integral here and you end your integral here by showing you have symmetric cancellation of your integrands, right? Because you can't integrate from 0, because it's going to be a natural log. And then ln of dy over y is going to be a natural log.
So where are we putting in the slope that we're getting?
I is a function of time.
Right, so like, where are we putting that?
3 seconds. You're going to pull your d by dt inside the integral and apply it to the I.
Okay.
Then that's a constant at that instant. It's not constant the whole time, but we're only asking for 3 seconds. The slope of that line is a constant at 3 seconds, just indicate a picture where 3 is. I'm giving you this number.
Why are we choosing to get the slope instead of the, just plugging in for a, because we have.
You can take the derivative right in there, and then plug in 3/4, that's fine.
Oh, like, why are we doing the derivative? Yeah, but why
Because
are we
it
doing
says
the
to
slope?
take a derivative.
Okay.
Because once you pull that inside, you're gonna have di by dt.
Mm-hmm.
I'm gonna take that, and I'm evaluating it at 3. Because that's what it asks me to do. Sometimes the answer is the simple thing. Hey, because it asked me to. Your second homework problem is 55. We want one last quiz, or should I tell you that this is homework?
I'm
What
surprised
difference
this
does
is
it make?
Surprise you. Oh, I like the surprise.
I remember.
A battery is connected to a series RL circuit at a time t equals 0. At what multiple of the time constant tau sub L will the current be 0.1% less than its equilibrium value? Told you you're not going to have to do this on the final, so I make you do it for homework. That way, when your transfer institution says, you didn't teach about RL circuits. Yes, I did. So, battery, RL circuit. Doesn't matter the order, right? Charging part, right? At what multiple of the time constant will the current be 0.1% less than its equilibrium value? So we know it's going to start with KVL and inspection, right? And you'll get this guy, E minus IR minus LDI dt equals 0. You'll solve that sucker, and you'll get this guy. I is equal to I maximum 1 minus e to the minus RT over L. Or, since the time constant always goes on the bottom, tau sub L is equal to L over R. Tau sub C for the RC circuit is R times C, but we talked about that, what happens in the oscillator when you switch one term for the other, right? They're mechanical electrical analogies. So if you want to rewrite it this way, what does it say? At what multiple of tau will the current be 0.1% less than its equilibrium value? How the hell do I know that?
You get its equilibrium value?
You don't need the equilibrium value. Do you?
Guess not.
What can I replace that term over there with? so that it's 99% at the equilibrium value without knowing what the equilibrium value is.
There you have it. Then you just cancel out.
Ta-da! Easy peasy. Second order, first rank differential equations. So basically, when you solve that, you don't know t and you don't know tau sub L. You'll get one in terms of the other. What's it asking for you? At what time, what multiple of tau sub L is that equal to that? You'll get a t equal to some multiple of tau sub L. Everything else will turn into a number. You'll have t is equal to something tau sub L. You're looking for that constant in front of tau sub L. I'm gonna knock that out in about 3 minutes.
You would knock it out in 3 minutes. I want to be in your office hours for 30 minutes, confused, in about a week from now.
So that's already posted.
Take some initiative.
Chapter
Confused
31.
tomorrow. Be confused tomorrow.
Chapter 31. April 6th. These guys have been open for 2 weeks already. So this is the stuff on the RLC circuit. This is the stuff that you will hope will be on the final, because it is pretty darn straightforward.
I don't hope that happens in the final.
You know, hope it's gonna be on the final.
I would like some kinematics questions.
Can you just be like a multiple choice, what is gravity?
Give me some kinematics.
Yeah, physics.
Kinematics?
Okay.
Question 5, LC oscillator. How do you deal with an LC oscillator in the realms of the basic idea?
Is this chapter 31?
Chapter 31, problem 5. What is, in an oscillating circuit, L is equal to 1.1 millihenries, the unit of inductance is the Henry, by the way, and C is equal to 4 microfarads. The maximum charge on the capacitor, 3 microcoulombs. Find the maximum current. I'll use Q for current as a function of time, and capital Q for Q max, because that's what the book does in this chapter. Right. Lowercase q means Q at some time, capital Q means Q max. So if it was varying sinusoidally, you'd see something like this. The Q at any given time is some ratio of the Q. And of course, it's going to vary sinusoidally, isn't it? Aren't we smart?
I'm not intelligent.
So we need a depiction. I like it. LC oscillator, right? There's no R, there's no E. Simple. Sounds like a loop rule coming. How do I know? Well, if I draw my pluses here, because one side of the capacitor has to be positive and the other side has to be negative, the current will flow in this direction, which means the voltage on the capacitor is positive minus the voltage on the inductor is equal to 0. Right? Now definitions. V sub C is Q over C. V sub L is L 1/2 L, no, V sub L. L di dt. Right? So substitute. that's a second order first rank differential equation. What? Di by dt is equal to the second derivative of q with respect to t. Because after all, I is dq by dt, right? So di by dt is just the second derivative of q with respect to t. Right? How do we solve that guy? Looks like separation of variables time, right? So if we rearrange, we do math. 7?
That's not seven.
Seven is always right.
Always says seven.
One of these sounds like your equivalence of C.
We have like 3 of these values, right?
I'm sorry?
We have like 3 of those values, right?
Oh, matter of fact, we don't need to do that. We don't need to solve it because we're only interested in maximum. Sorry. You
Nice.
simplified, right? So what this tells us, I don't need that part. My apologies. I was going to solve it more complicated. This is number 5. I should have realized this. This is.
Of course.
That's one of the first ones in the book, right? So this is true. The voltages are equal, right?
So we didn't need the double.
So we don't need the double integral. Let's get that stop here.
Ooh,
And
so the eraser's only so big.
It tells us that with these given values, that Q maximum is 3 microcoulombs. So now we're going to apply conservation of energy. The system is this one, right? The potential energy stored in the capacitor plus the potential energy stored in the inductor must be equal to some constant. Conservation of energy says, this in LC oscillator, is there any resistor in here stealing any of the energy away? Remember what the capacitor does? Stores energy in an electric field. What does the inductor do? Stores energy in the magnetic field. So we have a closed and isolated system. There are no resistors to suck our electrical energy away and make heat. Right? So the energy in the capacitor plus the energy resistor. By definition, the energy stored in the capacitor is 1/2 Q squared over C, and the energy stored in the inductor is 1/2 Li squared. We could have derived these, but I will let you do them without deriving them. We'll treat them as definitions.
on the test.
Yes, I will help you with that as well. If I'm not driving them in class, you're not going to drive them with this.
You're the best.
I know. Oh, sorry, it's a constant, sorry, not 0, constant. We are given Q max equals 3 microcoulombs. What's the consequence of Q being a maximum? That means it's got all the energy it can have, right? The implication is that I equals what? Not just a constant. 0. If all the charge is in the capacitor, there's no current flowing through the inductor. So how does it have any?
And doesn't.
When Q maximum equals 3, I equals 0. Oh, you're so close, right? So that tells us that 1/2 Q squared over C is the constant for the total energy of the system. Do I have Q maximum? Do I have C? C.
Yeah.
Spanish, right? So, substitute. That means the total energy equals 1/2 Q squared over C, which is 1/2 times 3 microcoulombs squared over 4 microfarads. Just call it T. 9/4, 9/8 microjoules. Get that right?
Sounded good.
3 squared is 9, 4, 2 is 8, 9/8. 1 micro cancels 1 micro is left.
So that's gonna be the maximum current?
Huh?
Is it the max current?
That's the maximum energy.
Never mind, I went back to the current stuff.
And now we say, hey, that's this constant. And I want I maximum. So what happens when I goes to I maximum? What does that imply that Q goes to? 0, because all the energy's in the inductor. So this constant, 9/8 microjoules, is equal to this term. Oh, that was really crappy. Equals 1/2 L times capital I squared. Don't you love these?
Sure.
You were given L as 1.1 millihenry, solve for I. You're done.
Solve for I.
Oh, yeah. 9/8 times 2 divided by L square root.
So we got I equals 0 before because all the energy's in the capacitor from Q.
And if you want the maximum current that can be achieved in the inductor. Now, this is a allowing ideal behavior. So in other words, the charge has to leave that side of the capacitor all before it reaches the other side of the capacitor in this idealization.
And assuming there's
So
no
you'll reach a
resistors,
maximum, exactly.
despite the fact that
There's no charge at all left
an
on the
inductor
capacitor in
has
exchange.
resistance, like the
Which
one-
there should be one instant where that does occur. It ramps up, it slowly transfers from one to the other. Because what the frig is this gonna look like? Physics 1, total energy. Energy stored in the capacitor. Energy stored in the inductor. Total energy constant. Does look familiar, right? There should be one point where one has the max and one has 0. Should be one point when one has the max and one has 0.
Here's how that works.
Crazy.
Just like physics one.
Just like physics 1.
That doesn't happen very often in this class.
Happens all the time.
No, it doesn't.
Yes, all the time.
No, it doesn't.
All the time.
I haven't seen F equals MA in too long.
I know.
I missed it.
I miss F equals MA so much.
Then they give you some examples. I won't bother to do them. Like 6, it basically has you convert a spring block oscillator to a LC oscillator. And remember how I told you in the RL circuit, the RC circuit, there's these electrical mechanical analogies. The spring constant is 1 over the capacitance because the capacitor is storing potential energy. You don't need any charge moving to have energy in your capacitor. So that's like spring potential energy. But the moving charge is needed to store energy in your magnetic field, you need the current. So that's like the kinetic energy portion of your spring block oscillator. So you can very simply create the correspondence. Don't you love it when I talk math? Remember that 1/2 kx squared plus 1/2 mv squared was equal to a constant in the spring block oscillator. Potential energy stored in the spring, kinetic energy of the one. This guy is akin to the capacitor. So you get 1/2 q squared over c plus 1/2 Li squared is equal to a constant. So you replace the m with the L, you replace the v with the I. You replace the x with the q, and you replace the k with the 1 over c. And you have the correspondence, the corresponding equations. Because the spring has energy simply by its position, the capacitor has energy simply by having charge on it. The inductor needs current to flow through it, so it's like kinetic energy. And you need a speed in order to have kinetic energy. The solutions are mathematically identical. So you can substitute one for the other. The same thing we saw for the RL and the RC circuit. Same exact equation, except Q has become I. R has become L, and C has become 1 over R. Yeah.
Is frequency and capacitive reactance inversely proportional.
When you, reactive capacitance is inversely proportional to frequency. X of C is 1 over 2 pi FC. But this is only for circuits that have a reactance, one with an external EMF source. So we're not talking about an LC oscillator, we're talking about an RLC circuit.
Is that one?
This is not. You can use this, but this guy behaves, the frequency of the oscillator is only like that when you drive it at the natural frequency. Remember the phasor thing I was discussing, that here's V sub R, here's V sub L, here's V sub C. That's the same as IXL, this is the same as IXC. If these guys cancel, your E is in line with your VR. That means XL equals XC, because with the same amount of current, it's a one loop circuit, it's the same thing as VL equals VC. That means 2 pi FL equals 1 over 2 pi FC. You move the LC over here, right? You keep the frequency squared over there, and then you get the 2 pi squared as well, equals that. So that's where you can see the frequency of the driven circuit is tied to 1 over LC is what the square root of 1 over LC. And the omega goes away when we turn that to omega. So that's where the omega equals 1 over the square root of LC happens in the LC oscillator. It has the same resonant frequency as the RLC oscillator based upon L and C, because the R then just determines how much current you get, not the balance point. The balance point is the same as the balance point of that. This guy, you drive though. You choose the frequency, and you may get resonance, you may not get resonance. This guy will drive itself. There's no resistor to interfere, so it's going to oscillate at that resonant frequency given by the same equation. It has to reduce to the same equation because it's the same circumstance. Good observation.
So since there's no resistor, that's why it theoretically just
Oscillates forever. Yep.
Assuming no energy is lost or something.
Crystal watches were based on a similar circuit to this. Back, they used to use winding watches all the time, and there was always some differentiation by how much it is. Then they went to crystal watches, and the crystal watch, the resonance set up in the crystal watch was tied to the size of the crystal, and it made very precise measurements. And so that's the way they used to have more precise timepieces when they went to crystal measurements of crystals of perfect size that would create a resonance in them. And every time that resonance distance was known, it counted that as the appropriate portion of the second. And it was not subject to mechanical variations.
Mechanical watches are cooler though.
Huh?
Mechanical watches are cooler though, they take.
Back in the 70s, Timex was quartz timing. It was one of those. Remember those examples?
Fortunately, temperature changes.
It does, but generally, if you're extreme conditions, most of the time your body temp keeps it relatively
watches and
You wear it on your wrist.
Apple watches and shit.
Yeah, very good point.
Well, why people still wear them?
Okay, so what will you be required to do with the RLC circuit? Something like this. Something like problem 36, right? You know, I'm always about understanding graphs, right, to help us understand stuff. They give us a transitional or transient, as they say in the circuits classes, a transient understanding. Rather than just, I can compare this point to this point, electricity doesn't just magically appear from one point to another. We need to study how the electricity moves. And so this is a transient based upon some variables. So we'll get to that picture in a second. I'll zoom this up so you can read the details more. An alternating source with a variable frequency. So you've got an alternating source with a variable frequency. So we draw that as a sine wave, but many times they draw it as a sine wave with a little line through it like this, indicating you can change the frequency. That thing is still used to some extent, right? It says it's connected to a capacitor and a resistor in series. So it's just a capacitor and a resistor. It doesn't have an inductor. It only simplifies the equation a little because the inductor part falls off. But we treat it just like a driven RLC circuit. The L will just be 0. So it'll have the same exact setup and the same exact solution, except mathematically simpler when we go to, remember we're gonna get this guy. We're gonna prove this is the case for an LRC driven circuit, right? We're gonna prove that from the phasor drawing, right? Once we get here, we're gonna say, hey, L is 0, so VL is 0, so it's going. It's just gonna make it mathematically simpler to solve, right? Okay? So.
Why do you have a line through your,
That
sign?
indicates it's a variable frequency source.
Okay, thank you.
That's old school stuff. I think, do they use it in circuits? Do they say that? Most of the time, sometimes. Remember, it was hard to do drawings back in the day, so they had to come up with simple ways to represent things that we can now do easily with symbols, superscripts, subscripts, and things. I know.
How
So,
dare they?
how dare they? The graph below gives the impedance of the circuit versus the driving angular frequency. So Z as omega driven. And remember, we can drive it at many different frequencies. Just like you did in your lab, except it was an RLC circuit, right? You changed the frequency, and you didn't get a graph of impedance, you got a graph of current. But we know they're related because we know that E is going to equal IZ, right? So while you've got a graph of I as a function of omega driven, they're giving you a graph of Z as a function of omega driven. But Z is just E over I, isn't it? So it's measuring effectively the same thing. The curve reaches an asymptote at 500 ohms. They used to call those modes. Going backwards. And the horizontal scale is set as omega ds is 300 radians per second. It's radians per second, it's not hertz. The figure also gives reactance x sub c as a function of omega d. What are R and C? So basically solve for R, solve for C. So that's all, let's do the graph. I'm going to do this as if it had an inductor in there. That way you have the most complicated form, which basically says, and then we'll just knock it out. That way you can copy that derivation to that point and then continue with the VL in there, okay? So we draw our loop, and what do? KVL, KVL, KVL. Inspection. Now, note, this would be E minus VC minus VR, right? Because that's all that's in there. If I add the VL, will it freak you out, or should we just do it this way? You put the VL in later? Which way you can?
I mean, it's gonna be zero.
Do it this way. Minus VL equals 0. Nothing wrong with saying that. If the VL ends up 0, it just runs 0 later, right? You would normally then try to solve them. So wait a minute, we got to draw our phasor drawing, right? Our phasor drawing says this is VR, and I is in phase with that. This is VL, and di by dt is in phase with that. Because of all these definitions I'm about to put up there in a second. Black marker. Can I use this one? I don't like whiteboard marker, it says, okay, let's go to show. VC. Because we know this one's longer, we're gonna say VC minus VL goes this way. We'll make our box. We'll make that our E, we'll make that our phase angle. Now when VL goes away, we know we got the right direction. Right. Could be the other way, but we drew it that way. How do I know that? Because VL is equal to L di dt, that's a definition. VR is equal to IR, and VC is equal to Q over C. We have a 90-degree phase difference between sinusoidally generated waves. You can pick any starting point you want. You can start with Q is equal to Q maximum, right? And then make an I out of that. Negative I cosine di by dt then is negative di by dt maximum sine of omega t plus the phase angle. You don't absolutely need this as long as you say there's a 90-degree phase difference because of sinusoidal nature, right? This is where you actually would prove it mathematically. Hey, I take a differential of Q, I get a 90-degree phase. Take a differential I, get a. Doesn't matter if I start with cos or sine. All we're looking for is the 90-degree phase, or that gives us that picture, right? I draw this picture because I see that, right? That then allows me to solve a quadratic solution based upon the triangle. That triangle there. Instead of E being equal to the sum of those three, then we get the equation. Therefore, E is equal to the square root of V sub L minus V sub C quantity squared plus VR squared. Because I'm inspecting my triangle. This is VC minus VL or VL minus C, it doesn't matter, it's squared anyway. And that's VR, right? To get my E. That's how I showed you to derive it in the first place, right? We're just repeating that derivation. Now we can put in VL equals 0. Why? Because L equals 0. There's no L in there, right? So you could have left it off to begin with, but I wanted to show you the base derivation one more time for the LRC circuit. No problem doing it that way, right? Hell, you could do it for the RLC circuit and make L and R both 0. L and C both 0. Then you just got friggin' Ohm's law again, right? Which is what you would get. And now we got to look at this stuff, right? Now we create the super loop. Almost out of time here. So that means I have a source and I have this reactive thing called the super loop, right? KVL. Sum of the voltages equals 0. This is my impedance device Z. I'm replacing all capacitors, all resistors, all inductors with one thing that takes them all into account. So by inspection, I get E minus the voltage of the impedance device is equal to 0. By definition, V sub Z is IZ, just like when we Ohm's law all these guys can be related to this one, right? We can convert those to VL equals IXL and VC equals IXC for a given frequency, right? For a given frequency. So you do the same for the impedance device. So that tells me E equals I times Z. And if I simply take E and divide it by I will get the impedance. So I take this whole equation and divide it by I. That gives me E over I is equal to the square root of VL minus V sub C quantity squared plus VR squared. This guy is now 0, divided by I. Make the I squared to pull it inside. Then take V sub C squared over I squared, you get X sub C squared. Take V sub R squared over I squared, you get R squared. So Z is then equal to the square root of negative X sub C quantity squared plus R squared.
Is the negative inside the square?
Yes. Doesn't matter. And now we have boundary conditions we can solve for, right? What happens to the frequency? Since the definitions, X sub C is 1 over 2 pi FC, and x of L is 2 pi FL, or in this case, I'm sorry, they give omega, let's use omega. 1 over omega C and omega L. And it gives us the information that I just erased, what did I say? Omega is the asymptote. Z approaches an asymptote
At 500.
at 500. Right? So given Z approaches 500 as omega approaches infinity. Right? So what happens to this equation as omega approaches infinity? I get 1 over infinity times c. What's that going to be?
0.
So as omega approaches infinity, x sub c approaches 0 as omega approaches infinity. That means this z equation now at 500 ohms, z equals r squared. So 500, square root of 500 equals r. Because x sub c is 0.
What is it, z equal to the square root of r
Oh,
squared?
it does. Square root. Square root. So r equals 500. Now to do the last of it, you just need to find one point where x sub c can be measured, right? Or one point where z can be measured. Here's a point. I think this is 50, and that's 500, right? So by inspection of my graph, I note that for omega equals 50, I get x sub c equals 500. So now I go back to the previous equation.
Is the x-axis omega d or is it just omega?
Huh? Omega d is 50,
Okay.
500. So then you put in x sub c, I'm sorry, x sub c, I don't need that one, I need the x sub c equation, my bad. I could use the z equation as well. I just simply use x sub c is equal to 1 over omega c. When x sub c is equal to 500, 1 over 50 times c. So c is 1 over 25,000.
Yeah.
Which I think is 40 or 4 microfarads. Whichever. What was your question back there? Sorry, somebody was.
How can you just like divide the I and put it inside of the
Because it's a single loop.
square root?
I of the capacitor is the same as the I of the resistor, same as the I of the source.
So you just throw
I'm
it
dividing by a
inside.
constant. No, it's changing, but it's always the same constant. This guy experiences the same current that the same guy this experienced, the same this guy experienced. So I might not know what it is, but if this is equal to this, and I divide this by the same number I divide this number by, that's perfectly allowed. I just choose the number I, so that the V over I will give me X.
Doesn't that
Because of the
number
definition.
change when it goes inside of it?
Yeah, you square it to pull it inside the square root. I inside becomes the square root, then you pull the square root inside the squared and it gets unsquared. And you simply get VL over I minus VC over I. That gives your X's. So we come back on Wednesday, I'll do one more of these, showing you the switch one. The switches are fun.
Oh, fun.
And then we'll move on to chapter 2. But the nice thing is we don't have a pre-lecture for. We're after the next problem. After this guy. The switches. Switch.
For differential equations, they decided to put a test Monday and a final Monday, Wednesday, or final Wednesday, Friday, and then the next Monday. It's like,
That
why
sounds
even,
awesome.
why even have a